Welcome to the Deep Dive. We're your fast track to understanding the key research in agentic AI. You've definitely seen how things like code interpreter and search really boosted what LLMs can do. Think ChatGPT agent, Gemini-Pro. Suddenly, they could write code, look
Yeah.
things up online. It was huge.
Oh, absolutely. A massive step up. Tool integration turned these models from just text predictors into, well, dynamic problem solvers. But, and this is the tricky part the sources dive into, there's this underlying weakness. For any complex question you throw at it, the LLM still kind of struggles. Like, what is the best way forward?
Right. Should it just reason internally? Fast, but maybe inaccurate?
Exactly.
Mhm.
Or should it spin up the code interpreter for some precise math?
Or maybe it needs fresh info from a search.
Yeah, and the real problem is the optimal path isn't obvious most of the time.
It's not like questions come labeled, use code interpreter for this bit.
Yeah.
So if just hoping one agent gets it right isn't reliable, what's the play?
Well, that brings us to tool use mixture, or TUMX. That's the framework we're looking at today. It's designed to sort of sidestep that single high-stakes decision.
Okay.
Instead of one agent making the call, TUMX basically runs several different agents all at once in parallel. And critically, these agents are diverse. They're trying different strategies, different tools simultaneously.
Interesting. Multiple bets instead of one big one.
Yeah.
Okay, so our mission today is to really unpack this multi-agent thing, how they collaborate, and crucially, how they get these, pretty impressive accuracy improvements the paper talks about without the cost just exploding. Because honestly, some of the efficiency claims sound almost too good to be true. We're really diving into the cutting edge of agent strategy here.
Yeah, let's get into it. First, why do we even need this kind of mixture? What's wrong with a single agent? The bottleneck, fundamentally, is that text reasoning alone is great for, understanding language, common sense
This
stuff.
epic.
Right. But it's terrible at precise calculations. Ask it a complex physics problem needing SMEPs. It will likely just make something up.
Hallucinate the math, yeah. Been there.
Or ask it for the latest news, who won the recent election.
Mm.
It might pull old, stale data because its internal knowledge is frozen in time.
Got it. So different tools for different jobs, but the agent doesn't know which job it's facing.
Precisely. It's like having a team lead who only ever uses email. Sometimes you need a phone call, sometimes a face-to-face meeting. Relying on just one method fails.
Good analogy. The input query just doesn't give enough signal.
So TUMX uses test time scaling to integrate code interpreter and search and manage that risk. Architecturally, the key thing is it uses a single base LLM. They tested Gemini 2.5-Pro, Gemini 2.5-Flash.
Okay, so not different models cobbled together like a mixture of experts.
No, exactly. It's one strong base model, but running multiple different strategies or agent personalities on top.
Gotcha. One brain, many approaches.
That's a good way to put it. And the diversity isn't accidental. It's designed. They created, I think, 15 different agents. Some were simple, like just a direct prompt or chain of thought.
Standard stuff.
Right. But then they added complex ones using tools. Dedicated code agents, dedicated search agents, even agents using both tools, and some guided agents with special instructions. It's this mix, this heterogeneity that gives the initial power.
Okay, so you've got this diverse team generating initial ideas or answers. How does ChemoPax pull it all together? Is it just a simple vote?
No, it's more sophisticated. And this is the second key piece. Iterative refinement. The agents don't just submit an answer and walk away. They basically have a structured debate over multiple rounds.
Yeah, debate. How does that work?
In each round, after the first, every agent looks at the original question and all the other agents propose in the previous round, their reasoning, their answers. Then, based on all that input, they generate a new, hopefully refined solution.
Wow, okay, so it's like intense peer review, automated.
Pretty much, yeah, taken to an extreme.
So we've got the structure, diverse agents, iterative refinement. Now let's talk about what actually happens during that refinement. This brings us to the role of diversity you mentioned. What did the results show?
This was a really interesting finding, and it sort of pushes back against some other work on test time scaling. They found that the diversity of the agents and their quality was way more important than just, say, sampling many times from the single best agent.
Hold on. So having a mix of different strategies, some text only, some code, some search, actually beats just taking your supposedly best agent and running it over and over.
Exactly. That's what the data showed. It contradicts some findings, like from mixture of agents, MOA, where repetition seemed key. Here, heterogeneity and quality won out.
That makes intuitive sense, though, right? Different approaches cover different blind spots.
Precisely. And they showed that agent groups that had both code interpreter and search tools available consistently got better results, better coverage, than groups missing one or the other. Those complementary tools are crucial.
Okay, speaking of coverage, this leads to a really fascinating trade-off they observed with the multi-round refinement. You said the agents debate. What happens to the overall pool of answers during this debate?
Yeah, this is where it gets subtle. So on average, accuracy tends to go up in the initial rounds, especially for the really hard benchmarks like HLE and M. The agents are successfully challenging weak ideas, refining
Okay,
things.
that sounds good. Accuracy up.
But, and this is the catch, if you look at coverage, which they define as, is there at least one correct answer anywhere in the pool of candidates? That coverage number steadily drops as the rounds go on.
Wait, how can accuracy go up while coverage goes down? That seems
Oh.
counterintuitive. Is the system throwing out good answers?
Essentially, yes. It's like structured peer pressure.
Ugh.
The agents start to converge on a consensus answer. Because they're all looking at each other's work from the previous round, the group gradually drifts towards whatever the majority is leaning towards.
Ah. So even if that majority view is actually wrong, the refinement process can amplify it.
Exactly. A plausible but incorrect consensus can emerge early, and then the continued refinement pushes everyone towards it, potentially discarding a correct but outlier answer generated in an earlier round.
Structured peer pressure. I like that framing. It means you can lose valuable diversity, correct outliers get squashed by the groupthink, you risk converging too early on something suboptimal.
Well, that's the danger. Over-refining can actually hurt performance by killing coverage, and it wastes compute, obviously. So this trade-off makes it really important to know when to stop the refinement.
Right. Which brings us to efficiency. Running all these agents, multiple rounds, sounds expensive. How did they tackle the cost, especially this problem of stopping at the right time?
Well, yeah, different questions need different amounts of work, right? Some are easy, some are super hard. Stopping too soon means lower quality. Stopping too late wastes compute and risks that convergence error we talked about. So they needed something smart, something adaptive.
And this is where, for me, it gets really clever from a practical standpoint.
Yeah.
They didn't just pick a fixed number of rounds, like always stop after 4 rounds.
No, they use the LLM itself, the LLM-as-Judge idea.
Tell us about that.
Okay, so after a minimum number of rounds, they enforced at least 2 to ensure some initial refinement. The system basically asks the base LLM to act as a judge. The judge looks at the current set of answers and reasoning from all the agents. It assesses consistency, confidence, basically asking, have we reached a stable, trustworthy agreement here, or do we need another round of debate?
So the LLM judges when the LLM's agents should stop working. That's delightfully meta.
It is, and very effective.
How effective? What did this adaptive stopping do for the costs?
It was pretty dramatic. Using the LLM judge achieved performance almost identical to running the maximum number of rounds, but it cut the inference cost down to only 49% of that maximum.
Wow. Slashed the cost by more than half, basically, with minimal performance hit.
Yeah. It's a huge deal for making these kinds of complex agent systems actually deployable.
It really shifts the focus, doesn't it? Scaling isn't just about more hardware. It's about intelligent control over the compute, surgical application.
Absolutely. But wait, there's more. They didn't just use the LLM to run the system efficiently.
Don't tell me. They used it to improve the system itself.
You got it. They turned the LLM into an agent designer.
Okay, now that's wild. Explain that.
So they took their initial set of 15 human-designed agents, which were already pretty good, and then they prompted Gemini 2.5-Pro, saying something like, here are some effective agent strategies. Can you invent some new ones that are diverse and high quality, maybe building on these?
So instead of humans engineering the prompts for the agents, they prompted the LLM to engineer new agents. Prompt architecting.
Huh, yeah, that's a good term for it. The LLM generated new complex agent types things like iterative planners, agents that could verify and refine their own plans. Quite sophisticated stuff.
And did it work? Did the LLM design better agents than the humans?
Apparently, yes. This pool of LLM-generated agents delivered an extra average accuracy boost of plus 1.2% on top of everything else compared to the best human-designed set.
Okay, that's significant. It shows a model can not only execute the process efficiently, but also optimize the design of its own components.
It's pretty profound, yeah. The model is improving its own strategic capabilities.
So let's bring it all together. We have diverse agents, iterative refinement, an LLM judge saving costs, and even an LLM designer boosting agent quality. What's the bottom line? how did this TUMIX perform on tough benchmarks?
The overall gains were substantial compared to just running the base LLM without any of this test time scaling. TUMIX boosted average accuracy by plus 7.8% for Gemini 2.5 Pro, and even more impressively for the smaller, faster Gemini 2.5 Flash model, the gain was huge, plus 17.4%.
Plus 17.4% on Flash is massive, and these gains were across benchmarks like HLE, GPQA, Diamond, AM, which, we should remind listeners, are not easy tests.
Not at all. GPQA Diamond has graduate-level questions designed to stump LLMs. HLE Humanities Last Exam is notoriously hard. Mixing deep math, science, engineering, getting any improvement there is tough.
So specifically on HLE, where the baseline Gemini 2.5 Pro was struggling at around 21.6% accuracy, where did TUMX get it?
The full version TUMX plus ROA pushed that accuracy up to 34.1%.
Okay, 21.6 to 34.1. That's a very significant leap on a benchmark like HLE. It really shows this diverse, tool-using, collaborative approach works for complex reasoning.
Definitely. It validates the whole framework.
But even at 34.1%, the paper mentions there's still a bottleneck, right?
Yeah.
Despite all this clever engineering, something is still holding it back.
Yeah, and it comes back to something we touched on earlier, the final answer selection. Even though the diverse agents generated at least one correct answer for over 65% of the HLE questions, that's high coverage, the final accuracy kind of stalled out around that 34% mark.
So the team of agents is great at brainstorming, at getting the right answer onto the table somewhere.
Exactly. Exploration is strong.
But picking the single best answer out of that pool of possibilities, especially when some are noisy or subtly wrong, that's still the hard part.
That's precisely the issue. Final judgment, aggregations, selection. That remains the key challenge for these test time methods. Generating good candidates is, it turns out, easier than reliably picking the winner.
Fascinating.
That's it.
So this has been a really deep dive. Let's try and summarize the key takeaways for everyone listening. The big message seems to be unlocking the real power of LLMs with tools isn't just about giving them the tools. It's about how you structure their use using diverse strategies, letting them collaborate and refine iteratively.
And doing it efficiently. That's critical. The quality of the agents, the strategy for how they interact, and especially knowing when to stop the process, like that LLM-Judge saving over half the compute cost. That's where the performance and practicality gains really come from. It's strategy over just brute force.
Okay, so that leaves us with our provocative final thought for you to chew on. If the LLM itself can figure out when spending more compute is just waste, saving all that cost, and if that same LLM can actually design better agent strategies than the human researchers started with, adding real accuracy points, then what does the future of scaling these incredibly complex AI systems look like? Is it more about humans crafting the perfect prompts? Or is it more about teaching the LLM how to become its own architect, its own efficiency expert? Where should we focus our efforts?